My name's Dave Kohake. I work as a soil scientist for the USDA Natural Resources Conservation Service. I'm going to try to go over a little bit of soils training here for some of the Envirothon students, just the normal stuff that we would go over during a normal competition. Usually we start with what is soil and what the definition is. So soil is the unconsolidated mineral and organic material that's at the Earth's surface that's capable of growing plants. So the big things to remember are just mineral and organic there at the surface that would be capable of growing plants. So obviously a rock or something is not capable of probably growing a plant, but if it weathers and forms minerals and topsoil and stuff, then you could start growing and you actually have soils. The importance of soils, obviously most of our food that we eat either comes directly or indirectly from the soil. A lot of the clothes and stuff we wear, the trees that we harvest for lumber for our houses and all of that, soils provide the foundation for most of the roads and houses and towns that we live on. Soils are important in filtering water. They naturally will take up pollutants and things that might be falling and filter water so we got clean water to drink. So let's just talk a little bit about why do we see different soils form in different areas. We basically have 5 soil forming factors that kind of dictate what soils form where. Those are parent material, climate, topography, the organisms or biology of the area, and then time. When we talk parent material, it would be how the minerals or material got to the spot. Either did it form from the bedrock that's sitting there, or was it brought in by the wind, water, glaciers, and that type of thing. So here in Kansas, we have different parent materials that the soil's formed from. Usually the easiest one to comprehend would be residuum. So that would just be soils that weathered from the bedrock there in place. So in Kansas, we typically have 3 prominent types of rock that soils weathered from. We'll start with like limestone. Obviously most people here in Kansas have seen limestone. You see a lot of fossils in it. We'd have certain soils that weather and form in that. We'd have sandstone that occurs in definitely northeast Kansas and definitely the central part of Kansas in places. And then we have different kinds of shale. Sometimes the shale you'll see in road cuts along the highway. It's often with the limestone in places, but all of these formed when the area was covered either by like a shallow sea or ocean, or like the sandstone was a beach that would have been, like this sandstone was from central Kansas. It'd be Cretaceous age, so almost 65 million years ago, or back when the dinosaurs roamed the earth. The shale you often see, typically shale is a softer type of rock and you can kind of break it up, and it comes in all kinds of colors. You see reds, grays and whites, and even organic type blacker layers in it too. A few other rocks that we might see, especially here, we're sitting here in the Flint Hills right now, is chert or flint, a harder type rock that's more resistant to weathering, and you see it throughout the Flint Hills here in Kansas. One final rock that we'll get to, we can have soils that weathered from glacial till. So we tend to see that only in northeast Kansas. So basically the Kansas River and the Big Blue, kind of that corner of Kansas up in there. And so these rocks aren't native to Kansas. They were brought down by the glacier. I think they'd say this was from like Minnesota type area. And then 600,000 years ago, the glaciers would have brought some of these rocks down and deposited them in Kansas. So they can kind of track how far the glaciers made it based on looking at the extent of how far those rocks come down into Kansas. So obviously those are kind of your main rocks that residuum type soils would form from. Another type of parent material we'd have would be ones that are more water deposited. Those would typically be along your rivers and creeks. We'd call that alluvium. And then you could have, maybe not so much here in Kansas, we don't see it as much, but lacustrine would be deposited from like old lake beds, that type of thing. Another one that's very common in Kansas would be wind deposited soils that weathered from material that was brought in by the wind. Typically that's called lusts, would be your silt-sized particles that have been brought in, and much of western Kansas has a loss. You definitely see it in the northeast part, like Doniphan County along the Missouri River bluffs, very thick deposits of loess there. You can also have sandier particles such along the Arkansas River here in Kansas that would be aeolian sands that were blown in and mixed in. And so the other common one would be the glacial till, like we kind of talked about. And then we also have what would be called colluvium. Well, that would be material that's moved down slope. So you might have soils forming up here on the higher part of the hill, and then you start to see thicker, deeper soils on the foot slope of some of those hills. So we have a soil called colluvium, or a type of parent material that'd be colluvium down there. Another soil forming factor would be climate. So obviously, depending on how much rain or your temperature, you get different soils forming under those different climate regimes. So soil in Alaska is going to be different than a soil in Hawaii or Florida. But even just across Kansas, we'll see pretty big differences in our soils just based on the precipitation gradient that goes from southeast Kansas that gets 40 some inches of rain to western Kansas, which is around 20. And then temperature. Kansas, you probably don't see huge differences in soil based on temperature, but obviously if you're in a tropical region, you're going to get soils that are more highly weathered than ones that are in colder Arctic type regions. Another soil forming factor would be topography. So you're going to find different soils that form either on the top of the hill versus the side of the hill versus down at the bottom of the hill. Also encompasses that would be like elevation and aspect. So in the mountains, you might see different soils on north-facing slopes versus south-facing slopes. Kansas, we don't obviously see that near as much. The fourth soil forming factor we'll say is like the biology or the organisms that are in the area that the soil that was growing and the soil's formed under. So here in Kansas, we were typically in a grassland setting, so we often see thick, dark surfaces at the top. And if you're in an area that was more dominated by trees and stuff, you'd see different soil properties form. So definitely as you go eastern U.S., you see different soils than compared to here on the where we had more grasslands. And the final soil forming factor would be time. So obviously if you have a rock or something, it's going to take it a long time to start weathering and breaking apart and forming soil. So most of the time we say, give or take 300 to 1,000 years to form an inch of topsoil. So it definitely takes a long time here. So let's just talk a little bit about soil horizons. So a soil horizon would be a layer that is approximately parallel to the Earth's surface with different soil properties. So obviously if you dig a hole down into the ground, you might have different properties here at the top versus you go down lower into the profile. So we'll just talk a little bit about the different horizons that we maybe would see. These are some of the monoliths of typical soils we see here in the Flint Hills. There's 6 master soil horizons that we describe. And I usually start with the O horizon, even though we don't typically see that in Kansas. The only time I'd say to be an O horizon, it would be dominated by decomposing plant material. So it's in an area that's either very, very wet and the decomposition rate's pretty low, or you'd probably see it typically more in colder climates than maybe Kansas. I don't know if we actually have a series here in Kansas that we have an O horizon on, but I've probably been on sites in which we did have enough organic matter at the surface that we might have technically had an O. But typically for our profiles in Kansas, we'd start with what would be called an A horizon. So that would be the zone which we'd often think of as the topsoil that'd be closer to the surface, that would have more organic matter in there. So you often see the darker colors on these different profiles here at the top. So those would be like an A horizon. Another horizon that we see, but I don't really have on these monoliths, would be an E horizon, and that's a horizon that's usually lighter colored, where clay and aluminum, iron, and things are leached out of the profile. So it's kind of a zone that's lighter in color that we maybe would see typically in wetter places. So if you went, even Missouri would probably have more E horizons. Kansas doesn't have a lot of soils that we describe E horizons on. But back to these, the next one would be a B horizon. So Kansas, we often have A, B, C type profiles. So a B horizon would be a zone where we've accumulated clay, carbonates, gypsum, different things, and moved in the soil profile and concentrated in a zone. So in most of the time when you dig a hole, we tend to see an increase in clay. We've had clay that's moved down in the profile. So like this profile, these would be clayier than what the surface would be. And then like this one would have carbonates and stuff throughout the profile. Then after a B horizon, we'd often see like a C horizon, which would be a horizon which hasn't had any soil formation really occur. So it's usually lower in the profile where water isn't necessarily moving through it. This that hit the shale down here at the bottom would technically be a C horizon. And then the final one is an R, which you can think of as for rock. And so when you actually hit such a rock like this is a profile that's shallow to limestone. And so this would be an R horizon once you hit the limestone. And we can go right into soil depth here, because these would demonstrate it pretty well. If you got a soil that's less than 10 inches thick to a root limiting layer, so when we say soil depth, we're talking about to the depth the roots could go down into, and we would call like a limestone layer definitely root limiting. This would be, if it was less than 10 inches, it's very shallow, or 10 to 20 inches is a shallow soil. And then if you got a profile more like this one, if you got a profile that's between 20 and 40 inches, it's called moderately deep. And then these other ones, if it's greater than 40 inches, you have a deep profile. And we have started, if it's greater than 60 inches, it would be very deep. Let's just talk a little bit about different properties that we see in the soil, and we'll start with physical properties. So those would be the ones that we could actually probably see and feel. Let's start with color would be an easy one. We have a color book that just has different colors that would be typical of soils. This would probably be soils across the whole Midwest or US could be used for this. And then all you do is hold it up to these color chips and be able to color and describe what the soil is. The books are used, obviously, my eyes might be different than somebody else's, and if I want to communicate with a soil scientist in another state or country, if you describe the soils in a uniform way like this, they would kind of know what color you're talking about. Let me move this real quick. So one of the biggest things, obviously, when we go out and look at soils is the soil texture, which would refer to the sand, silt, and clay percents that are in that soil. So when we talk about texture, we're talking about the sand, silt, and clay. And so the sand are the biggest soil particles. And when we say big, it's less than 2 millimeters. So they're still pretty small. Anything bigger than that goes into rock fragments like gravels and clear on up to boulders. But when we talk about sands, it's the typical, what we'd feel for a sandy soil. You can see when you make a ribbon with sand, it doesn't hold together very well. Sands don't have a lot of, or don't hold a lot of nutrients and that. So if you have a really sandy soil, such as, you know, maybe down by Hutchinson or the Sandhills of Nebraska, you'd have to do a lot of fertilizing and stuff to grow plants and stuff there. but obviously water moves through sand very quickly and easily, so that's one benefit of sands. The next size is silt, so that's sand particles you could see with your naked eye, but silt is getting down there small enough that you'd have to have like a microscope to see it. But silt usually feels floury, or I think it feels a little bit like Play-Doh if something's real silty, but it'll tend to ribbon, and you can see that it'll hold together to some degree. So it's definitely, a lot of our better soils seem to be higher in silts. Water moves through it fairly well. But again, it wouldn't hold a lot of the nutrients that are needed for crop growth. When we're talking about clays, those are the particles that you'd need a microscope to definitely see. Clays, when they're dry, they're very hard and cloddy, and when they're wet, they're very sticky, and they would ribbon very easily and stick together like that. Obviously, if you had a soil, clays that would be very hard to work. They get hard and cloddy, and they're very sticky, especially when wet. But clays would hold a lot of water and nutrients that would be available for crops. So ideally, we'd be looking for a soil that kind of have a combination of all those, so water can move through the profile easily, but it's got some clay to hold that stuff for. Another property that we'd look at is like structure. So how are the soil particles kind of arranged or held together? Usually like near the surface, especially when it's in a grassland or rangeland setting, the soil falls apart pretty easily into small little aggregates, and we call that granular structure. So water could move through that granular structure pretty easily. When you get lower in the profile, like some of these would be, when the clay picks up, we'd have something that would be more like subangular blocky or angular blocky, where it breaks apart into bigger, coarser type aggregates there. We'd also have soil structure that would be like prismatic or columnar when you get lower in the profile, are pretty common. And then obviously when you've got compaction or tillage, we'll see platy structures. So then you've probably seen it like in a wheel traffic zone where the soil's very like laid together like plates because it's been compacted down. Another physical property would be consistence, and that would just be kind of the how, if you applied a force to a soil, how hard does it take, how much force does it take to break it? Obviously very dependent on the sand, silt, and clay. I think it correlates pretty well with that. An additional property would be the available water capacity, just how much water would the soil be able to hold that would be available to plants. Dictated a lot by the texture, the organic matter, and like how many rock fragments would be in the soil. Usually the highest like silt loam type textures would hold a lot of water. So something that's more, the clay particles might hold a lot of water, but it might not be available for plants. Usually we're looking for something that's more like in the loams or so. A final physical property would be the permeability, or how easily water moves through the profile. Definitely the sandier the profile, the easier water moves through, and the more clays, you'd have slower movement through it. We'll talk a little bit about the chemical properties and start with the pH. So usually for our soils, we'd like a pH roughly near neutral. Usually that's when you have the most nutrient availability. When you get a soil that gets more acidic, in the 5s or so ranges, it would affect crop production, and we often would need to lime, which would be adding like calcium carbonate to the soil to up that pH to a level that would be more conducive for plant growth. And pH also affects microorganisms and that type of thing as well. An additional chemical property would be the cation exchange capacity. So that would just be the ability of the nutrient holding capacity of that soil. The more clays you have, the higher the cation exchange capacity would be. and vice versa. Sands would have a lower cation exchange capacity. And we'll talk a little bit about just the nutrient status. Obviously that could be affected by adding fertilizers and stuff, but certain soils would naturally have more definitely nutrient holding ability, but definitely more nutrients in there. When we talk about that, we're usually talking about like nitrogen, phosphorus, and potassium. So when you buy a bag of fertilizer, you often see NPK on there, and it would be telling you how much of that is in there. Soils also, we also talk about salinity and sodicity, which would be how much salts or sodium would be in the soil. Both more detrimental. If you have high salts, it can affect water uptake and things. So obviously we prefer a soil that would be low on salts, and definitely a soil that's low on sodium as well. Sodium can affect clays and things, and it can make for poor soil structure and water movement through it. Another chemical property we could look for is redoxymorphic features, which would be signs that there's either water table or water movement through the profile. And so we often look for, if you see things in your soil that are like concentrations that are like red, rust-colored stains, you often see grayer profiles and stuff, you might have an indication that there's a water table or water in that profile. And then finally, another chemical property would be like the carbonates in the soil. So we have certain soils that are this weathered from calcareous shale. So we have a lot of calcium carbonate in that profile. And when you do have a lot of carbonate in there, we have a good idea that the pH of that soil would be, near 8 or in that range. Finally, we'll just kind of briefly go over biological properties. Soils are alive, so there's a lot of microorganisms and earthworms and gophers, moles, all kinds of things that are going through your soil. When we think biology, you could probably throw organic matter in there because it kind of affects, it's obviously biological, but it's affecting chemical and physical properties in a major way. So organic matter would just be the plant and animal remains that are decomposing in the soil. Highly weathered organic matter is often called like humus, and it definitely affects the nutrients, water movement, soil structure, and all that, and it usually for a beneficial way. So the higher organic matter in the soil typically would be a higher, a better type of soil for farming and all. So quickly we'll talk about soil erosion. That would be obviously when soils are leaving the area where they formed there. We often talk about water and wind. So on the eastern side of Kansas, which usually the concern is more water erosion. So you start to see, we have different types. It'd be sheet, rill, or gully. So sheet would be just simply this particles just kind of slowly moving over the top, and then once they start to concentrate into small little, we call them rills, you'd start to see little, a rill would be an area that you could farm. It's not deep enough that that you couldn't farm around it. You could farm through it, but you just keep closing that rill shut. Well, once that rill gets big enough, we start to see gullies, and those would be obviously bigger areas that you couldn't get equipment through. On the western side of Kansas, we have more wind erosion concerns. Obviously they get less rain. I'm sure they get big rain events and get some water erosion, but obviously they have droughts and dry weather and get wind erosion and that out there. Quickly we'll talk about wetlands. I deal with wetlands quite a bit, and they do provide a benefit. They would storage during flood events, wildlife benefits. They're storing the water there, so they're filtering out certain things. So wetlands do provide a benefit, and We typically, to be a wetland, you got to meet hydrology, soils, and vegetation type requirements. So hydrology, you would need a water table that'd be close to the surface, that would be, you know, ponding water and stuff at times. Soils, we would need a hydric soil, so we have certain indicators. Typically, like I showed before, grayer colors with these rust-stained concentrations in places, and typically close to the surface, so it's indicating that that water table is right near the surface. And then we'd look for wetter type veg like cattails and willows and things that typically grow in wetter places. So we'll finish talking up a little bit about soil mapping. Soils are predictable. If they weren't predictable, we wouldn't be able to map them and kind of identify where they're occurring on the landscape. And we kind of talked about the soil forming factors, so those are all dictating where those soils are at. But soil scientists before me, you know, walked the land, dug holes, checked different landform positions, and then they drew maps and drew out where the different soil types would change. And so this would be the Wabaunsee County Soil Survey. It's got a lot of good information in it. Now what we do, though, instead of trying to update or go do these, we can update soils using computers, and we have what's called the Web Soil Survey. So then you could, if you had a question about what soils are mapped in your area, you go on the Web Soil Survey, zoom to your area of interest, and identify the different soil properties that might be important that you're interested in. So that kind of concludes the soils part of this Envirothon training. Hopefully you learned a little something about soils, and good luck on the Envirothon.